Okay, hey folks. We're going to start in just a few minutes. We're transitioning from our stand-up meeting, which we just ended, to the research meeting. So just give me a couple of minutes. I just wanted to come live and let you know that we're about to start. I don't think you can hear anything except me right now. I can see the office, but I'm not going to turn it on until they're ready. So I'm just going to get to stare at me in my office for a few minutes. The paper is linked in the description down below if you want to take a look at it. This is like a series of paper reviews we're doing for Numenta Journal Club. I hope you guys are enjoying them. If you are, please be sure to like the video and subscribe to our channel. We're doing this just about once a week. We're trying to do it once a week, so that's my agenda. You can ignore that. But I might be live streaming later today on some of this stuff on Twitch if you want to check out there. But yeah, so just bear with me while the team sets up on their end of the live stream. Okay, we're waiting for a PDF to be sent from one place to the next. And yeah, Cerebro 3. Do you remember Cerebro 1 and Cerebro 2? Cerebro 3 from the same person who brought you Cerebro 2. So just bear with me a minute here. We're almost there. We're just trying to get a version of the document that's marked up already so it can be displayed for you guys to add emphasis to whatever we're talking about. Hello Cody, hello Chris, thanks for joining. I don't know why my chats sometimes works. Chat test, is this working? Yeah, showing up. Sorry about the wait. Hi Martin. Yeah, we have a podcast. It's Numenta.com. Search for it. There's a podcast there. I do episodes of it. I'm going to do at least 3 more soon. I'm just sort of planning them out. But you can find that already. It's called Numenta on Intelligence. The Numenta on Intelligence podcast. All right, we're getting there. We're almost there. Real close. We're so close. Hold on, guys. Okay. We're live.
Okay, and if you want to, if you want to scroll it and stuff, you can do it from here. So, and as you can see, it's a separate monitor for me.
Okay. So I have to look into the essentially.
Yeah.
I'm gonna turn my mic off, you guys, so you don't hear the traffic.
Oh, let's see. Should I open this in a different reader? I can open it up in Acrobat.
If not, it's okay.
No, I should be able to. Sorry.
I'll take it off your screen, Marcus, just in case.
Oh, I mean, at this point, okay. Sure. At this point, I'm sharing a certain window. Okay. How do I do this? Files. Probably drop the computer. Please just work. I hope you. Acrobat Reader does not support drag and drop.
Accidentally sharing something like an email, personal email or something. It's not cool.
You can, if it's a professional version. You pay extra money, maybe it does support it.
You can attach code that you want. You could just code it.
Yeah, so for the podcast,
So
it looks like that.
Podcast, I'll be talking with Sudatai about current tech.
Okay, so you'll be able to
tactics
do everything you need to do.
Yep.
And then I will change which window I'm sharing, or I'll just change.
And what we think we're going to be able to do with it.
We are almost actually starting.
We're getting close, guys.
Now we have annotations and everything. And yeah, we can start.
All right. Okay, we're good. Thanks.
Thank you, Marcus. And well, so I hope you read it too, in the sense that I have not went in depth. I mean, on this, I'm not one of the authors of this, and just as a disclaimer, I mean, I do my best to try to summarize the basic ideas of this work, but feel free to interrupt and join the discussion, and we'll see where it goes. But essentially, this paper is studying essentially the idea of sparsity and the importance of sparsity in the context of continual learning. So I guess that this idea of sparsify of the connections, the weights, and the activation, so having representations that are sparse, it has been around deep learning, machine learning for many years now, and many people they think that this is important for several reasons, right? For generalization and to avoid overfitting, but I think this is one of the first works, and this was published at IACLR 2019, that tries to really go more in depth about sparsity and continual learning in the context of continual learning, how this can help learning continuously. And the basic idea here is that if you have a neural network, right, with a fixed capacity, the gradient descent optimization often leads to an oversaturation of all the entire network when you learn from a specific training batch. As
by oversaturation, you mean interference?
Yeah, I mean that all the weights somehow there's a very natural balance and delicate balance among the contribution of each weight, right? It's not that you learn from a few images, for example, a few examples, and you use just a portion of this network.
Right.
You always use all you can about the network. And another interesting idea that has been around is that, I mean, if you increase the number of parameters, even though the problem is the same, actually you get better results just because of this over parameterization of the network. This is something has been explored a bit, and it's also cool that from a network that is over parameterized, you can also distill the knowledge to another smaller networks and still being able to reach the same level of accuracy. So essentially, you could always find also for the pruning works, etc. This idea, I think that this idea of over-parameterization is inherent the concept of gradient descent itself, the optimization that comes with it. So it's helpful to have this hugely over-parameterized network in general. But the problem, especially for continual learning, is that you saturate the whole network since the first batch, since the first piece of data that you have. And so the idea of this work was to say, okay, let's take a step back. As we know that we're gonna encounter a number of training batches over time, we can say, okay, let's also penalize our ability to solve a particular task in a particular point in time, but let's preserve some space into the network so that we can allow later on to encode new information in the same space, in the same parameterized space. So that's the title. What the title is about: the idea that you don't want to be selfish when you learn a specific task. You want to think ahead and be more generous with respect to the other tasks' performances, I guess. And so where is the pointer here? It disappeared. Here we go. Okay, and essentially the basic, I guess the paper is about a comparison with other regularizers and activation functions, how they impact on this process. But essentially, they propose a new regularizer, a new sparsity regularizer, let's say, that is already taught for continual learning, essentially. And it's based on very loosely inspiration from biology, in the sense that they try to inhibit surrounding in a specific region of the entire activation space neurons that activates at the same time in nearby locations, essentially. Okay, so I thought it was very interesting. I mean, it's a very good paper, I think, and it's very easy to follow. And I really enjoyed the introduction. Some people, especially in the open review platform, this is you can find the reviews online, thought that the introduction was maybe too long or something. But I think it's quite nice and interesting. You have a lot of references here pointing out different concepts in the sparsity literature, I would say. And and I think something I would also to discuss with you is the idea of sparsify the representations and disentangling them somehow, and the idea instead of sparsify the weights, the connections among these neurons. So that's
in our case, it's not very similar, but we have something related with the K-winners we started talking about, and although it's not implemented, we have this notion of K-winners with local inhibition, and that would end up in the same end result as they did, but the way it does it is using regularizers, which just adds a term to the last function.
Yes.
In our case, we have this global activation function, which picks the top K-winners.
Yeah.
And right now it doesn't have local inhibition, but I think Luis is working on that, so it also do that over regions.
Exactly.
So in that case, I think the end result would be very similar.
Yeah. So just.
And I think it's in this paper. I think it's very interesting. It says it compares just sparse weights versus sparse activation, and they say that if this is manual representation, sparse activations make a lot more sense than sparse weights. Which if you have sparse weights, you have the end representation. Sparse representation of what makes sense. Sorry about that.
No, that's
making a parallel.
Thank you. And so what I don't remember my own comments. Sparsity is key for decorrelated representation. Yeah, that's also very interesting. That the idea that with standard gradient descent, you have very entangled representations, and every weight is essentially, if you look at the importance distribution of the weights, you can see that some weights are more important than others. But essentially, these, if you look at the histogram, you see that still, even for small tasks, small data sets, you use more than 50% of weights that are important for that particular task. So that's interesting to see, and so it will be. I mean, this whole idea of decorrelated representations and possibly also weights, it's super interesting for continual learning because you want to compartmentalize things so that you don't run into interference. Sorry.
But this idea has been from before, right? Like this idea of just picking up calculations which corresponds to a decorrelated representation. So you get like the Paris matrix, and then you just pick the ones which are less correlated with one another, has been there for a long time. I think the difference here is that he combines that regularizer with also a sparsified regularizer.
Yeah.
So he combines both. So you get disentangled representations with regularizer.
Yeah.
And he makes the case that
Exactly.
in order for them to be really disentangled, they also have to be sparse. That was, I think, the key addition of the paper.
Yeah.
Like mixing these both ideas, sparse and disentangled representation through a decorrelation.
So okay, this is just an image, a cartoon image, I would say, on the idea of sparsifying the parameters, so the connections essentially between neurons, and then representations. And they argued that essentially the sparsity of the representation is more important for continual learning in this case, and to disentangle the knowledge essentially that we encode into the network. And what is this about?
You can tell by your highlights that you like to be interdimensional.
Okay.
I really like page 6. Really good.
But I suggest you to read the introduction. It's very nice, and I can now read my own comments here. But that's okay. I don't think you can click on it. It just
More comments.
no. Okay. Well,
I can take a second to try to.
sometimes it's working. Sometimes not. I don't know.
How do you do this? Sorry, maybe. Oops. And comments. How do you? Oops. Maybe not. I thought this would have a way to view like an outline.
Yeah.
Or maybe it's. Never mind. I guess I'm not finding it. I thought there would be a way to just like see the.
Well, no problem. I don't.
100% view or something like that. Yeah.
Yeah. Awesome. Okay. Sometimes it works. Okay. So why sparse activation rather than sparse parameters? Essentially for two different reasons: more stability and the fact that then you have free neurons to use later on. Question that I already asked you: why do you think parameter sparsity is useful as well? Since in your model, the cortical learning algorithm, especially, I know that you already explained in the paper how can be so dense, but essentially you didn't use structural sparsity of the connections, right? In the paper, there's an image in which you show that sparsity can be both.
Oh yeah. So in that paper, it's both. It's both weight sparsity, parameter sparsity, and activation sparsity.
Oh, but it's fixed sparsity though.
Sparsity. It is, yeah.
So, but I read in a sentence in this in that paper, you said that for convolutional kernels you didn't use.
No, but Sutai is rewriting that paper, and now he's using sparse and convolution.
Okay, so it was just for.
Yeah, we're just not. I think he said it was not clear at that point how to apply weight sparse and convolution, and we could discuss. It makes a lot of sense to apply between channels.
Okay.
Because if you change the filter itself, then you have
not this filter, but the connection. Essentially, what kind of feature maps you're looking at in the input volumes.
Otherwise, if you change in the kernel itself, you're changing the kernel. You're changing the
Yeah, it makes sense.
It doesn't make a lot of sense. But still, we have bunch of papers that work on unstructured pruning. That's just like pruning at random over the kernel included. They work fine, and I run like a bunch of experiments using unstructured pruning, and they work fine as well. So if you also apply sparsity over the kernel, somehow it works. Even though if you think about it intuitively, it's
You're destroying the semantics of
destroying the
these
semantics,
filters.
and it wouldn't make sense, but it kind of does. So it's an open question.
Okay.
Well, if you think about it, if you come down to a lower level and you say, I have a corner detector, you don't necessarily need a perfect circle of detection out there to kind of give it the idea of a corner.
Right, that makes sense.
So, I mean, there's in SIGGRAPH or 2 back, they basically were using ray tracing and they found that they could lower the number of samples they had to do and then use machine learning to deduce what the rest of that structure would be and amplify upon it. So, you know, if you take it from a pure single processing point of view, it would be anathema to, you know, lose pieces of that. But if you're looking at it to say, what's enough of a structure for me to recognize it at this micro level, then it's legit.
Then another thing is that these kernels are generally very small. So 3 by 3 kernel, it's different from, I don't know, 16 by 16. And then in that case, maybe there's more space for sparsity there and what you were saying.
And the amount of sparsity applies like extreme. So if it's a 2 by 3, you have 9 units, and then you apply 10% sparsity, but you have 1 unit.
Yeah, but if, for instance, if it's looking, if you're just saying, I just want to, you know, compute the derivative, you just need 3 of those 6, of those 9 to get a hint of the thing.
Right.
So,
Yeah, at some level, sparsity still makes sense. Right? At some level.
yeah.
Okay, and but essentially for what I can remember now, they work on the sparsity of the representations essentially in this paper. And so the main proposal is this sparse coding through local neural inhibition and discounting algorithm.
Let me add discounting.
We'll see now as they did a very nice progress towards this final, let's say, proposal.
There's a good translation study.
Okay, this is the main, let's say, proposal, and then they, of course, assess the performance of these algorithm on 3 different benchmarks, I think, or maybe 2, and NIST and Tiny ImageNet. Right, and Cypher, yes. Okay, so three of them. Contribution, okay. So essentially, 3 contributions: study the diverse set of representation-based regularizers, parameter-based regularizer, and as well sparsity-inducing activation functions to design. Okay, then the proposal, and then the empirical evaluation. Okay, so I think there's a lot of different proposals in this area. I mean, sparsity in general for continual learning. Maybe the other paper we also suggested reading for today is using that concept as well. But I don't remember any other continual learning paper, at least to the best of my knowledge, working specifically on sparsity for continual learning. Even though I guess that it was something that many people were thinking about, as because it's well known this capacity saturation factor. So it's basic idea to have more space is to have little weights that are important for every task, right?
I think Marco has more.
Okay. Yeah.
Continual learning, she has more. That's a good thing.
Okay.
Is there formal definition of capacity?
I don't think there's something standard there, but some people have proposed. For example, the other paper from I don't remember the name, but essentially the other paper we are going to look at. Yeah, they for example they propose a definition of saturation of the network And then they say that when you reach that kind of saturation, you want to gracefully forget, essentially. And they explain how you want to do it.
Which paper was that again?
Continual learning via
Okay.
you're gonna look at it fast, I guess, because I explored it even less than this one. So, okay, so no, what happened?
Did you do these notes in Mendeley?
Yes, exactly. I thought that it was the most portable.
Probably. I don't know. I can take 2 seconds to see if I've installed Mendeley in this computer yet. Yes. But I have not opened it yet. If we want to take 2 seconds, just so that this
Yeah. I mean,
will probably be worth it.
meanwhile, we can.
Nonetheless, you get like a
So
mobile app. So do no surgery. Mendeley has like a mobile or tablet app. I don't know.
I think so. But the nice thing is that they have every paper that you have is uploaded online too.
Right.
So you
But
have.
the competition.
Okay.
What
So
it has,
what are the
like I
alternatives?
used to use the Witka. Widcube had this app, but then they just like mess up and I was really bad.
It's difficult to annotate and read the papers on a smartphone. At least for
Right,
me.
that's what tablets, like I used to do.
Yeah, that was great.
And then I'm using all this stuff, paper file.
Okay, take 3.
Let's see if you can see the notes now or not.
Let's see what you'd be.
This
you know,
note. This is a note, right?
Yeah.
Or maybe not. Maybe.
Yeah.
Let's
If you can.
see this.
If you can just try and however you normally do it.
I don't know.
That's, I think, because you're
I
in
think it's not.
select mode. If you change to just the pointer thing, then maybe.
Oh. Where's the
It's
point?
on the very left, you have a drop-down menu.
Okay.
There, you select.
No.
No, okay, maybe that's not it.
Maybe there is a view all those, something like that. The view.
The hell
Isn't
is
this one
this?
Okay.
No problem.
Sandy, check.
Journal Club and Mendeley.
Okay, looks like we're gonna go back to this one and.
Yeah, and then if we are lucky enough, we're gonna see some of them. But it's okay. I remember
Okay.
most of them.
Try is paper.
Yeah. The PDF portability is still an issue in 2019. Essentially here you can find some interesting read about sparsity and algorithms that try to decorrelate activations of neurons for different patterns.
Can I cover just a second? I have a question, maybe Flora and Marcus. So we have something like that in the brain. Is decorrelating the activations a way of sparsifying, or we don't have any mechanism at this time?
That's very interesting.
So, I mean, I would say that, in general, activations of the brain are obviously quite sparse for whatever reason, right? But there are also brain areas that specifically do orthogonalize and sparsify codes, like, for example, the hippocampus, which is really important for memory acquisition,
Right.
particularly long-term memory acquisition and then driving the consolidation process, has an input area called the dentate gyrus, which has been studied a lot with respect to its input and output dynamics. And it's known that it essentially, its function is really sort of a pattern orthogonalizer. It makes highly separable representations of the input activation of entorhinal cortex, which might have a lot more overlap, and the sort of what comes out of there for the actual sort of memory encoding process, if you think of the deep structures of hippocampus of that, are a lot more pattern separated, allowing you to learn independent episodes and for memories to not interfere with each other.
Right.
But that is in part because hippocampus is a very small brain area, right? It's like 2.5 million pyramidal neurons in the main autoassociative field where then you learn patterns by recurrent connectivity with highly plastic synapses, which then encode that pattern. And even then, that's a transient process, right? So the hippocampus does forget, and through the consolidation process, like eventually becomes irrelevant. So there are some brain nests where people have looked at the input-output characteristics and have deduced that, yes, this brain area mostly does, like orthogonalization and pattern separation. So those do exist. I don't know how widespread that is. I mean, I've studied it with respect to the dentate gyrus because I actually built a little, piece of a network simulator thing that did that for a hippocampus simulation that was part of my very first paper. But I don't know what you would have to say about that.
Like, all I can say is that I have seen models that do it, models that have decorrelation of unit activity in general. So that individual units are decorrelated with other ones, but these are all just models. So it's like people have found reason to publish papers suggesting this happens, but I can't really list the neural evidence right now. I can't list the actual neuroscience evidence.
Right.
It very likely happens, but all I've seen is models.
And the follow-up question is, have we looked into that in our own models? Because even if you're sparsifying, you might
say, have we looked into it in our models?
So if you're explicitly trying to decorrelate activity.
Yeah, so yes, Mergo worked on something called lateral pooling, which was taking the spatial pooler and giving it this extra property where the individual mini columns try to decorrelate with each other. So he did work on that project for a while. Superset would be better at summarizing it than I am.
But that's not currently implemented in exam, right? That's not part of.
It'd be sitting in in HTM research somewhere, and it's one of those projects that.
Right.
So some experiments we've done on that.
But if you are seeking for specific papers on dentate gyrus or mini columnar competition, I'm pretty sure I can dig up 2-3 good review references.
Yeah.
Just remind me, it's like a 5-minute hunt for the right references.
Okay. So let's look at these specific proposal then. Well, essentially they start with a summary on the technique. Essentially, they also used, they proposed is memory-aware synapses in 2017. And it was essentially very similar to what we discussed in a previous research meeting about regularizing approach for continual learning. So the idea that you have, for example, a specific loss function that you want to minimize, let's say a concentric loss function for so f of theta n, and I guess here is the task, the current task you want to solve. So you have the standard loss function, try to minimize the prediction error, and then you have plus another term here that is going to regularize the continual learning process essentially. And again, as we have seen before, this is tuned essentially with a static real value here.
Right.
That is
Lagrange factors.
Yeah, and then what you have here is an importance value for each weight k, omega k, times the optimal value of the weight for the previous task and the current weight you're trying to modify, the same weight, right? So it's k that you're trying to modify and to move in the direction to essentially reduce this loss, right? And the idea is that as you move far away from the optimal weight of the previous task, and this weight is very, very important for the previous task, then this loss term is going to grow, explode, right?
Yeah. You penalize changes with a square, and every change is then also weighted by
Yeah.
the importance, meaning important weights can change even less.
Exactly. So that's the concept, and it was shown in 2016 by elastic weight consolidation, a proposal from DeepMind, and synaptic intelligence from Ganguly here at Stanford, and then their own work, our own later on. I mean, many people they somehow worked into this idea of regularizing learning over multiple tasks or batches.
So the importance is those are just fixed constants.
Yeah.
Make a case.
So this is fixed, right? The lambda term here is just to say how much you want to weight somehow this fact of remembering the past, or just learning about this particular task, the current task, right? So this is like saying, okay, I want really to remember previous stuff. If this lambda omega is I.
Yeah. What about lambda k? Omega k.
Lambda omega, right?
No.
Omega k is instead what in general it's the difference among the different strategies, in the sense that you want to how you compute the importance of each weight.
Omega is important. Yeah, no, I get that. I'm just asking, is it fixed at the start?
No, I mean, it depends also, but in I don't remember their own proposal.
So it changes over time.
It can change, or it can be, you can have multiple of these regularization term for each, as you can see, for each task.
But the whole idea is that at the end of training, you can calculate the importance of each weight.
That's right.
That's omega, yeah.
And then it carries over to the next.
Right. So in the next task, so if it carries it for each k is the task. So you always know that when you stop training that task, you know the importance.
I guess it's
at that point.
it's
So it's calculated
task.
after.
So you do a learning step and then you recompute.
And then you recompute the omega.
Okay.
And then how you recompute the omega is what changes between all those different things among them.
So is the tension between tasks just pairwise, or can they actually take an aggregate of number of tasks and apply this to it?
One task at a time.
Right, I mean, you have the previous one, then you have a new one.
Yeah.
But so it's basically kind of looking at it either pairwise or sequentially pairwise when you put new things on in. But does this generalize to saying, I've got in learn task, I want to add one more to it?
I think this is already general, this formulation, because this is for the task n. And so essentially you want to sum over
This is the generalization step. We sum over all the other
for each task.
I'm not sure.
No, each parameter.
Task.
For each parameter here, but then you want to add I think is the number of tasks training inputs. No, this is
Right.
training.
The number of training inputs for
Yeah.
each task.
Yeah, this is that. So you're adding the regularization term for all the tasks you have in the data set that you have seen already. So if you're in task 8 and you've seen 7 tasks, you're adding a regularization for all the previous 7 tasks. So this term is a summation of each task.
Okay.
It looks like a summation over the parameters.
Yeah,
So
I guess, but
right?
it depends if in that importance it's somehow like we do, for example, if that importance term is taking into account all the possible, all the previous tasks together, then you need just one regularization term. Otherwise, you need multiple of them, right?
I see.
I don't remember exactly how they do it, but the original proposal from DeepMind was to have a regularization term for each task. So as you move on, you add regularization terms on top of each other.
Oh, okay, so there's.
So essentially, if you move, this is for the second task, let's say, then you move on the third task, you need to add another regularization term that is relative to
Okay, so this thing is, there's this series extends.
yes.
Okay. it just-
Or you can compress the importance value as you said, you can say, okay, let's say that I am in a situation in which I consolidated the weights. So I consolidated the weights for all the previous tasks. So then I can think of say, okay, now all these weights are preserving already the information. I'm assuming that. So now I can say just for the new task, shouldn't disrupt the previous, let's say, weights.
Okay, so when you.
But you have still to maintain the importance somehow of also the previous tasks.
So that consolidation step bothers me a little bit because under what basis do you consolidate, say that I can fuse these things together?
Well, at least the assumption that we did was that you can essentially sum this importance over, in the sense that you want to what you want to preserve as much as possible the weights that have been important in the past, and that cannot change. It's like freezing these parameters after a while, right? So if they have been, the idea is if they have been important in at least a few of previous tasks, then you want them to not change, right?
Right, but when you say consolidate, that to me implies that you're melding things together and doing a compromise.
Yeah. So for example, if you think a simple sum, what we do is a simple sum plus a click factor and a few hyperparameters or something like that. But the idea is that empirically, if that weight has been important for many tasks, this importance value is very high. It reaches the maximum, and it means essentially that it's not going to be changed.
Okay, so what I'm seeing is what's being made is a statistical argument, as opposed to I identify the structure of these tasks and preserve them. I'm going to assume that it all kind of falls on out, that on average this thing is important, but that assumes that there's no, that these can be treated as independent attributes, as opposed to there's something iconic about this particular combination of this subset of parameters that if I start melding things on in, I just diffuse
You lose the dependence between the importances.
That's a strong assumption to make, right? That they are independent and
one
is not.
Yeah, hence the problem of consolidating them, right?
Yeah. So that's what I'm saying is that I think there's room to examine that assumption and seeing if that's actually valid or how much you lose by doing it. I don't know whether you would like partition the parameters in some arbitrary way, keep them separate, and then say how much loss do I get when I repartition these things or something like that.
Yeah, it's it's always an ongoing debate in the sense how much structure you want to impose into the network, and how much you want that to find itself.
We have a very structural model to go from, and we're trying to kind of melt it down.
Yeah, and also this proposal itself is very. I mean, it's something that is, especially from a math background and perspective, it's very nice. Because you have just a loss function in the end to optimize without imposing any structural
it's a recognized
constraint,
From the neuroscience perspective, it's not nice because you're basing that on a global function.
Yeah.
There's no way to implement that.
The brain is doing that, right?
Yeah.
So we should be aiming towards the local. Right.
Okay, so this was the basic idea of essentially controlling forgetting through regularization, pure regularization, and but then the original proposal was to add an additional regularization term that was let's say controlling the sparsity of the representations at all possible layers. So it was called RSSL. And then they say, okay, now let's go deep into this because you can implement it in different ways. So the first proposal is this one, where essentially we are looking at, in a specific layer, H of L, you have several neurons, H activation, something, H by M. Well, M is just, the number of inputs we are considering while doing this. We can ignore this, but the idea is that you have several activations, and you look at all the possible combinations of this activation in the layer, and you're saying that if you have more than of one essentially active neuron, then this regularization term is growing in terms of
It's just a dot product between the vectors of activation.
So essentially, you are saying this regularizer is 0 just when one neuron is active. And this is a basic idea to how to.
It's just like a sum total overlap of the activation set.
Yeah.
All possible combinations of your activations, and you just do dot products and sum them up, and then for normalization you divide them by the capital N.
Yeah.
So if you had 20 different ones, then you divide by 20.
Yeah, and it should be a bit more independent about
I mean, that's very naive, straightforward. Minimize the total overlap between all the patterns that you're using.
Okay.
It's called the Frobenius norm of the covariance matrix. What?
Well, this was the idea, but then they said as an improvement on top of this, it's not just sparse coding to neural inhibition, but it's to local inhibition in the sense that this was too harsh, they said. And so they tried to regularize it with another term here.
The problem is, the problem with that one is that if you have even one unit is coactivated with another one at the same time, it's activated at the same time as another one, you have a regularizer. So it's going to enforce the network to just have
maybe it's just too much. I mean, for neural networks to have just
one unit
to be forced to be that sparse. So probably, I don't know, they wanted to, as you also are doing, instead of just having a K winner at the top of all the volume of activations, you want to have maybe a few activations, but scattered around all the volume.
And that's the solution there, right?
There's also to be still a very principle. I mean,
So how does this one work?
And in the sense that you want to wait.
The further they are,
Yeah.
Exactly. The further they are from the two activations that you consider every time, the further they are, less weight. It's gonna sum up to the loss.
The further they are from what? Their distance
From each other, I think.
For each other.
like if this is unit 1,
E and
unit
J
10 is
units.
over here, and they're both active, then that's fine. But if unit 1 and unit 2 is active, then that would be a bigger penalty.
This is very, beautiful mathematically in the sense that it's very continuous. It's a continuous, importance problem. Instead of having, fixed region. So you let essentially the optimization problem solve, these compromises that you're looking for.
And it justifies basing how the brain works. Right? So the local inhibition is also property. Right?
Well, I think that the brain probably is much more structurally doing this, right? Instead of finding compromises between constraints that you pose. It's much more. It's already there in terms of structural constraints. I don't know.
What do you mean by structural?
In the sense that it's not like you're putting constraints and then you say, okay, now solve the problem globally with these constraints. It's much more, the constraints are already embedded into the in the local parts of the systems. They are independent among each other. It's not there's not something going on. I think that is globally taking into account all the possible constraints and
It's like a more local constraint.
yeah.
That kind of goes against your point that you said before, recently in this paper, but the loss.
It makes it more biological, right? It's arguing that look, if the fall off of connection probability for the disynaptic, feedback, the feedback inhibition is an exponential decay off. So maybe you have local, probability of well and 1 in their case, right? If the difference is 0, that you're guaranteed to have the full penalty, right? And then it decays off with an exponential term, which is, obviously not exactly how a real neuron works because, at like a meter out, the connection probability is not some very small number, it's actually 0. So it's a physical limit to how big a neuron can be, but it's a decent approximation of the axonal, and I can dendritic, overlap over space, right?
Yeah.
Connection probability roughly decays exponentially in the brain.
Is that true?
Yes.
And just keep
Nice.
in mind that that's still a regularized to the global loss. I get that, yeah. Okay, even though you add this local inhibition part, it's still regularized to the global function. Yeah, I guess it's true.
Yeah,
I
that's
feel better if there was not just a one-dimensional function there.
Like an exponential.
True.
No.
No, that's-
Exponential's fine, but this thing has an analogy to certain filtering algorithms that basically say,
Right.
I'll include this sample if it's close to A, the value that I started with, and B, distance-wise. So you basically have this kind of saying what the neighborhood is. But this is a neighborhood in an arbitrary, cutting along, these things, as
Yeah.
opposed to a two-dimensional one saying, yeah, I've got this cluster here, and there is some reason to believe that these things behave similarly.
Right.
So that's what bothers me about that one.
It linearizes brain activations as just one vector, as opposed to, as we think of it as a 2D sheet at least.
Yeah, like a one-dimensional case in that sense, then? Like, I don't know. it's
Well, but
some sort of abstract-
everything was two-dimensional up to this point, and then you flattened it.
Well, the thing is, it's
Well,
already flattened as the activations, right?
It
No,
never
I-
was a 2D model, right?
No, I mean, I don't know if it said somewhere. I didn't notice that, but maybe they are just talking here for simplicity on it. They talk about hidden layers. So I don't know what they mean by hidden layers in this case, because I've seen in their experiments
Right.
on Tiny ImageNet, they have also convolutions and
Right.
So on and so forth. So I don't know if maybe somewhere in the
if there is
appendix there's
spatial
an
structure in
explanation
the-
how to expand this
There is
from
not,
one to
I
the
got that,
Okay.
there's not, I was thinking about that. I
Uh-huh.
didn't see it.
Or,
No, maybe it's before, spatial locality. Like,
Well, but
idea
you
that-
can have spatial locality in a 1D array.
this is for an array of activations.
Yeah.
So how the distance is computed when you have a 2D or 3D.
Right,
Right.
3D.
Oh, is it same for like an image or something like that?
Yeah.
Use standard line happiness or something.
Yeah.
Oh, yeah. Because then it should be more like a 2D shape than one.
Yeah, I mean,
Is that-
to the extent that neocortex is two-dimensional.
It's a shape.
Well, but yeah, I think these are great details to explore, but the idea is, I think it's clear enough here.
Right.
Wait,
I
what's
don't know.
wrong with this? Because they go through another one, right? Yeah, there is a discount.
Yeah, and then there's I think that I will see the results, but essentially they wanted to, of course, use the knowledge that you already formed in the past.
Uh-huh.
So essentially, you're saying, and they want to form as well new knowledge. So you want possibly new neurons to acquire and to recognize new patterns, right? And they've seen that with this particular implementation, loss function as it is for now, if you move to other new patterns you want to learn from something, and essentially these weights that have been already trained, these neurons, they tend to fire again and to inhibit somehow all the other weights. So you have the same problem that you noticed as well, I think, in your paper, with this idea that a few units, they become very active for many different patterns. Because they tend to, as they fire faster than the others, because they have been already trained to recognize patterns maybe are similar to the new inputs, then they inhibit all the surrounding activations. So their idea was to introduce this discounting inhibition factor in the same. This is the final updated regularization term.
Good summary.
Yeah, exactly. Yeah, but essentially, they estimate the importance of each neuron, looking at the gradients flowing through them, essentially, and after they have understood what are the activations that are important, then they say, okay, just don't. If these activations were very important in the past, just don't count them into the inhibition
This is because the regularization
factor.
term for the continuous learning, the regularization time for the elastic weight consolidation already is gonna penalize that, right? You don't want to like double penalize. I think that's kind of the idea.
No, you still the weights that leads maybe to these activations are preserved, right?
Right.
The problem is that you cannot I think learn new things because these weights are very active, and they tend to inhibit new activations, new activation of different neurons nearby, especially.
You want to learn new way. Okay, yeah.
I mean, in a brain that doesn't happen because resources are finite, right? So you have synaptic depression, which like depletes transmitter, for example. And you have neural adaptation, which means that neurons that are too active are going to be inactive for a while. You have refraction, which means that a neuron that just has fired cannot immediately fire again. There's like shit tons of mechanisms in the brain that make sure that no resource can be overly important and overused. There's a biological limit to how fast a neuron can fire. I guess that
this is
a lot of these limiting factors in the biology, right?
I think this is just an alternative to your boosting algorithm in the sense that, but maybe no, boosting is much more, as you said, more biologically inspired, I guess, because it's modulating.
So homeostatic effect, at least that's what you use to motivate it, right? The way that you implement it is the way,
but
simple, but it does the same job, right? That's
I think in this case they are kind of cheating a bit in the sense that the more you go on, the more activations you're gonna, the more the less sparse you're gonna be in terms of representation, right? Because
there's a limit to that.
So let me see if I get that exact formula though, right? So there's these alpha terms which stem from measuring summing up some magnitude of gradients, which is some metric of importance. And then they sum them up I and J, so I don't fully understand. Like I understand the full rest of the term. I don't that's fine.
That's fine. This is fine.
The exponential is also fine. The one before, right? The new one.
I think it basically says the more important.
So the new one is this.
Yes, exactly. So that I would like to understand.
You look alpha I and alpha J are the importance of the two neurons you are considering. The new one, these two activations.
Or the ones between which I want to update the weight. And
no. These are not pre. I don't think they are pre and post synaptic. They are in the same layer. These are in the same layer.
I don't understand.
Like the set of activations out of a linear layer.
Right.
That's what the ING is. Like this is activation 1.
Right. That's their position. Right.
Yeah. So,
but then I still don't understand why that term looks like how it looks.
I think those are not numerical exponentials, aren't those selectors that in turn?
M term, kind of like.
No, M is you want to compute these on several input patterns.
Right. So
M is the number of
patterns. It's just a selector.
M is that.
The only other term there is the first exponential. Right?
Yes, this is the new part with respect to what we discussed before, where you want to, based on the, so if these weights, or one of them is very important to, no, sorry, they are not weights, they are activate neurons, activations.
I and J are nodes, they're not weights.
If the weights of the activations.
They're not weights, it's activations, right?
If the weights that compute those activations are important, is that?
No. This is all about the activations. It's really not taking into account the weights.
Wait, but I think alpha is defined here. We accumulate the absolute value of the gradients over the given data point. So alpha is the accumulated gradient. Right?
Okay, but
so
it
becomes a term for the importance of a node.
Neuron, of the neuron.
Well, they call
The
it
way of
neuron.
looking at it is if you separate them exponential, it's basically they're multiplically inhibiting each other.
Yeah.
So that's, rather than just looking that they're summing, they're.
Oh, right, that's the way to understand it. Thank you. Now it does make sense. Right. Right.
It's equal to e to the negative alpha I times e to the negative alpha.
Right.
They have to both be strong.
Basically.
Right. You're adding up in the exponent, so it means that it's essentially they're both factors.
Yes.
Right. And so you factor the exponential importance of both of those nodes negatively to impact your now new RSLNID, which does not just punish the overlap between patterns and weigh those spatially, but also discounts that set punishment for nodes that are really important.
Yes.
Wait, oh,
Perfect.
discounts them
Perfect
for-
description.
Yeah.
Discount their importance? No, it would.
It discounts inhibition if they are important. Is that what we're doing?
It would discount inhibition, but it would encourage them to be active if they were important, correct?
That's what I'm thinking.
Just a reminder for you watchers,
If they were
please like the
important,
video.
they didn't
If you
have an
enjoy this
impact
content, just give
anymore.
it a thumbs up.
Yeah.
So if a node is very important, right,
It's more likely to be active.
then also
Well, it's not the likelihood to be active, it's whether it's gonna be
Penalized.
penalized, whether the weights are going to.
then that term is going to be smaller, meaning they are less likely to get penalized in the minimization function.
Yeah.
Right.
Okay, so it's
Okay, I get
quite
it now.
interesting, quite interesting proposal. And then we can start looking at experiments. I think that they are not really convincing. I mean, there's a quite an improvement.
Can you
but not
explain just the legend here? I don't know what I'm
So yeah,
looking at here.
just wanted to give an introduction. So essentially, I think the first version was of the paper was not that focused on the empirical evaluation, and then they added what the reviewers asked them to, and then they become much more substantial. And now we have here 3 different benchmarks. So MNIST, CFAR, and Tiny ImageNet. So if you work with them, but I guess they are still considering a maximum of dimension that is 64 by.
And Tiny ImageNet, what is CFAR 100?
Okay, so
It's like CFAR with 100 examples.
Right, but what is CFAR? I'm sorry, I'm not a machine learning guy.
CFAR is just like an image data
It's a
set.
data set.
Yeah, with like just like a.
for object recognition, all of those are
Okay,
benchmarks for
It's
objects.
a training data set.
Supervised.
Supervised,
training,
yeah.
Okay.
And then you have for a few classes you want to distinguish, and
Right,
then
and 100 means there's 100 classes
Exactly.
to differentiate. Okay.
for MNIST you have 10 classes, from Tiny ImageNet a few more, but still you are working on a input dimension that is going from 28 by 28 grayscale, 1 channel, to a maximum Tiny ImageNet that is 64 by 64 times 3.
Right.
So this is the kind of input dimensions we are working on. And I feel that
Times
still
3 because it's RGB.
is RGB, right?
Okay.
So I guess I would have preferred them to use Core50. This is much more complex to see if it's really scaling this idea. Yeah, exactly. Oh, but that you want to scale a bit up this experiment, because it's not really clear to me why. I mean, they work that differently among each other. We can see that now. But essentially, here what you're seeing is so for MNIST, the results on MNIST of different sparsity, let's say regularizers, activation functions, and their own proposal. When you see 5 different tasks on MNIST over time, every task has to distinguish among 2 different digits of the MNIST data set. I'm sure you have seen that, but you have written digits, grayscale, and for every task you want to distinguish 2 different digits.
Right.
And you move on to the next. I think the it's permitted MNIST.
It's
Sorry.
permitted, that's the-
Well, it's not what I said. then.
They just change the location of every pixel, and then that's just a new task. So like
So the whole training
Right.
set, you have a fixed permutation of the pixels, and
every time you permute, then it's a new.
that way you have kind of the same complexity for every task, but it's a completely different task for a machine to solve. And
Right.
But why do you describe it's iCipher, it's then iCipher? So Cipher is what you describe, like you train in a field of the classes. And
Yeah.
other
Okay,
classes, but
okay.
then is here. Is permitted.
okay,
But so that I see the different colors on all these different regularizers, and on that y-axis you have some kind of an accuracy metric.
So this
I guess
is the-
that's a performance score of some sort.
accuracy. Yeah.
But then, so this is just on MNIST. This is not the other 2.
This is on MNIST,
Right.
and this the accuracy for every strategy on every task at the end of the training in a sequence of all these tasks.
Right.
And here you can see, I don't know why they didn't put here another, let's say, a few bars here with the average. and they put it in the legend here. But essentially, you can see here in the legend the average accuracy on all the possible tasks.
Good use. I like it.
I mean, it's much more clear if you have the average, the
They
bars.
could have at
with
least
the
like
average.
aligned the numbers, it's like.
Yeah, for example, I don't know, but yeah, well, so in this case, I'm sure I put a note here about the fact that it's not really significant here.
I mean, I guess the point is most of these methods drop off at the third, fourth, and fifth.
Why
But
is
they
that?
do have a bit of competition with like, what is the green and the orange?
That's a
Decoff and L1 regularization.
So yeah,
L1 rep.
so what it's the most interesting, at least to me, is to see the difference with respect to the basic relo activation. In the sense that, okay, and then another thing that I criticized about this evaluation is that you can see there's no comparison with a static training on the data with the regularizer. So you can't really tell if the improvement is because it just for neural networks it's just better to have sparsity, or it is useful specifically for continual learning, right? I don't know what you think about this, but if you don't have an upper bound saying, okay, with this sparsity activation function, you can have this kind of level of accuracy, I cannot say that this algorithm improvement is just about continual learning or because it just trains better.
There's some ablations in there. They do
Okay.
another section of it, maybe.
Sorry, what's technical? You're
Yes.
saying how would you? Just you're saying like train with sparse activation.
So I would like to see how all these possible activations and regularizers impact on the final performance of a model that is trained on the wall training set or
He has a
although-
quote here in the ablation series that SLNID improves the performance considerably by more than 4%, even without importance weight regularizer. This is the sparse part.
No, that's okay. That's okay in continual learning with this setting that they tested their algorithms. But what I'm saying that maybe these regularizers of their own, even in a static training, so not in a continual learning setting, would have brought essentially advantages. And this is saying, okay, yeah, it's cool to use it because it's better, but it's not really helping me in the idea of disentangling, the impact of these algorithms proposal, especially in the context of continual learning, right? I don't know if it makes
But I
sense.
don't think he makes a point that sparsity helps in regular training. He makes a point that helps in continual learning. That's the point.
Yeah, I know that
I think he
there
makes
was.
the first point, so.
No, what
I just don't think maybe he didn't want to make 2 points at the same time.
I mean, it's like I don't know. Let's say that we don't have convolutions. Then I say, okay, you have these tasks. It's quite interesting in continual learning. Then I say, okay, I'll now introduce convolution for the first times, and then I say, okay, it works much better on continual learning, convolutions for continual learning. And you say, oh, okay, that's cool. But if convolutions are working great also on a static training set, it means that convolutions by themselves are great for learning, not for continual learning. I don't know if it makes sense.
You see, you want to actually see like how this sort of regularizer performs on a static case.
Yeah, I mean, to see if maybe they just better, so the accuracy in the end it's better because they are just better in general.
Yeah, I want to see that too.
And I see that also reviewers they pointed out some of it. Then they said, yeah, well, the point is working on continual learning. Okay, but yeah, one of the reviewers said that, and
I mean, I guess the bigger question to the field is, right, given that continual learning is an additional challenge to a system, like you don't know all of your data up front, you have to acquire it on the way, right? Is there an actual penalty for that, right? I mean, it's clear that, many systems can't do that, but if you build a system that can do that, does it actually, how much of a performance impact do you get for building a system that's,
You're gonna like the second paper.
Okay.
The second paper they cover that much more.
okay.
I
right.
just point out that your answer is here, no? Task one. You only look at task one, then you get that. Right, and you can see it's not
Ah,
Not better.
no, but no, actually, this is the end of the training of everything.
Ah, okay, all right.
So you cannot tell that, but you cannot tell that. No, you can't. In this, there's a in a later experiment in this paper that in which they assessed the performance on all the training sets, trained together in a multitask fashion, joint multi-train. I don't know how they call it, but it's just one place you can find this information, but not for every possible experiments that they did. And I think this is it would have been very useful, at least for me. And yeah, then another thing is that for feminists, I don't know. It's not really. We are talking about a difference of 3 percentage points in the accuracy, so it's not really easy to tell. I mean, it seems like on this scale that it matters,
Right.
but I mean, I don't see that they have done several runs on it. I don't think it's an average among the different runs when you change the
At
order
least
of
they
things.
indicate no standard error.
Yeah,
right?
exactly. There's no standard. There's anything. So I don't really. I don't know how useful it
I mean,
is.
like the whole figure seems a bit hasty, right? Like in the sense that, well, just how it looks. And yeah, I don't know, like I probably would have made the font size on that axis bigger and whatnot. Yeah,
I
we
don't
talked
think
about
they
the
like number of tries or anything like that.
Right.
Like the average over.
That would be interesting to see the standard deviation, to see if really that 3% it has a value per se, or
Right.
it just not really that interesting. But yeah, of course, yeah. I mean, many people. We also discussed this in EURIPS 2018 in a continual learning workshop. People were saying, okay, don't use MNIST for continual learning because it's really difficult to tell. But even for deep learning in general, I mean,
Right.
now you have so little space for improvements and for for
Right.
understanding. It's just not. I mean, it's useful for maybe for yourself when you prototype something. You say, okay,
Because
that's a
it's
cool
not
idea.
runs on a laptop.
Yeah, exactly. But
But
then when you want to convince someone else of your idea, you just have to scale them up. And nowadays,
Right.
I think it's not, at least on 64 by 64 patches of,
I mean,
images.
you would hope, given that, like, I don't know, people are throwing around big terms like AGI and whatnot,
Yeah.
that we can go beyond, little, what is it, 32 by 32 grayscale
Yeah.
pixels.
28 by 28.
Then another
Not
big-
even that, okay, 28 by 28 pixels, okay. Like you would think that we can go make the world bigger than 28 by 28 pixels.
It's the distance between MNIST and AGI is so close. How big is this?
No, another problem here is in this particular setting of the MNIST, where you have this permutation. Essentially, people have. I don't know if they have shown it. It would be nice to show it in a paper, but we all know that essentially the network can change just the first layer to learn the permutation, and then everything is fine.
So,
Right? So you don't have to learn a new task. You just learn the permutation.
That's a good point.
just
So
to
it's not really
understand
interesting.
how radical is the permutation? I mean, I've not visualized it.
It's completely random
Yeah,
permutation of
random,
pixels.
Move the pixel like.
Okay, well,
So this first pixel goes always in this particular location.
So why is it-
the other way around?
so
But-
why does it progressively seem to get worse on some of these things?
Yeah, this is train at the end. So at the end you train and you see how much you still remember the first, second,
I
third
see,
part.
okay, got it.
That's that right? Right.
I think so, but I was
You
Yeah.
can correct me if I'm wrong.
But after the first permutation, if there was any spatial correlation, it's destroyed, so what, these are really adverse things to try to learn, right?
Right.
I mean, there was coherence in the first one, that's
So that's the whole point, that
No,
we're trying to
right.
learn completely different tasks. So that was the goal initially, right, when you created this. And-
right, but then if you keep on permuting it, then it's like, okay, I'm just trying to learn stochasticity or something, I don't know.
It's like you're trying to learn completely different tasks. That was the goal. Just think of it as like the
Yeah.
task number 2 is completely different than task number
Well,
1.
if you take MNIST and do a permutation starting off, and then make the rest of the permutations of that sounds a little bit better than what, this thing seems like a cliff that you're jumping over.
I mean, I think that's because that's the goal. The goal is like, can you learn completely different tasks with the same network? That's kind of the goal. In
I
that,
don't think it's fair.
right? There's not this notion of transferring like learning from one task to another. It's just like, can you learn completely different stuff? And you still remember like the first one you learned 8 tasks ago.
So per task, the permutation is the same, correct?
Yes, so it's fixed permutation per task, and then the next one is some other permutation.
Okay.
And they're supposed to completely change the structure of their task.
Yeah.
Okay. I'm not arguing in favor of this, I'm just trying to explain it.
No, I understand what you're saying.
It seems like an idiosyncrasy of the machine learning field, but there's nothing.
Yeah, a completely
It's
different
different.
task in the same class, I think would be a better thing than something that just basically says, as you say, just learn the permutation.
Oh, we can, there are sci-fi results we can talk about.
Yeah.
Sci-fi is a more interesting task because you have.
Can you read this line here? Because I was thinking.
Percentage after learning all tasks.
Sorry,
Accuracy percentage after learning all tasks. Yeah.
oh, but it was why the, let's say, average accuracy is decreasing like this. So why
Because
the
when
most?
you're learning 5 tasks,
Okay, but this
then
should be the
the-
most recent one, right?
But in this case, the regularization is, yeah, it doesn't make a lot of sense when there is no, yeah.
It should be the opposite,
Should
right?
be the opposite. I mean, at least in the one without the regularization for the elastic. weight.
well, maybe they're only testing, when they mean all tasks, they only mean
Considered up to that point.
up to that point.
Okay.
So T1 is learning all the T1 tasks,
What
right?
is-
So how good is the network with one shot
Yeah.
learning this one task? And then T2 is, okay, what is your performance after learning T1 and T2?
So in that case,
I don't think it's
what
that.
you say, if that's the case, you can say, as you
Right,
said before, you can tell by the first task how they are different
Right.
in terms of performance on a static train.
But I don't think it's what you said, because it says after learning all tasks. So it's supposed to be all tasks, not
Yeah,
all
yeah,
tasks. after-
yeah.
Again, it's a shitty figure, so it suggests that they also did not put in the time to properly think through their access labels and their legend, which does not explain that.
It's
So
not explained in the text.
it's,
Okay,
yeah.
but maybe I'll look more into that. But then this was the same.
How are they really trying to make figures that are unreadable? I mean, this is projected on a giant screen, and like you still need to zoom
Yeah.
in like crazy to be able to read it.
But that's the cipher split.
Maybe you take out the bookmarks or something.
So this is a very task that you get this data set like cipher and ImageNet, and you split between categories or classes. So you first learn 10 classes, then you learn 10 different classes, then you learn 10 different classes. So this would be
This is more
Better
what I thought, right? So this trend is much more.
it makes more sense.
It makes more sense.
So wait, what is the T1? Is that task 1 or time step 1?
Task
That's
one. So in this case, you have 10 tasks for, I guess, with 10 classes each.
Okay, right? Because it's 100 classes in
Yeah,
the C5
and,
data set, right?
But tiny image is just 100 classes.
No, maybe no. This is for CFAR on the
Right,
left, on the left, and then for tiny ImageNet split, I don't really remember how many classes. But in any case, in this case, they say that essentially the improvement now is over no regularization at all. It goes from 4 to 8. So 4 in the CFAR, I guess, experiment, and 8 in the the opposite. Sorry, 8 in the CFAR and 4 for the ImageNet, tiny ImageNet benchmark. So I always thought I tried to look into the paper why that was. I mean, it's a big difference.
So by split,
Why-
I'm basically saying that I've got 100 classes or whatever, CFAR, 100 classes, so I want to create, 10 sets of tasks that, I split the categories on up and I'll just trade against.
Right.
Okay, and so at least they're kind of in the same space.
Second one is the same, but it's 20
I think
per-
maybe we are reading the grammar of this y-axis label wrong. Like maybe, like it says accuracy percentage after learning all tasks, but maybe what they mean is accurate percentage after learning all tasks.
So period, and then you said all times.
You put a period.
Right. So the question is, right? Are they learning all tasks? Because it makes no sense if there's 10 different tasks, right? So then T1, so what is shown is the accurate percentage after learning, and not after learning all tasks, but they show the accurate percentage of all tasks after learning. And all tasks is not all tasks because it varies from T1 to T10.
Wait, no, not really. It's from T1 to T10.
So my understanding, at least, of these is still that, well, you're doing continual learning. So you're learning task 1 first, and then you're learning task 2, and then you're learning task 3, right? And by what they're plotting here is accurate percentage after learning, and not learning all tasks. So they evaluated all the accuracy after learning, but they evaluate the accuracy after learning, a certain number of tasks.
Well, I think
Because why else would you get like a drop in performance, whereas the T1 is amazing, and then it shoots down, right?
I mean, I think that for all of them, they still use some kind of regularized, like memory aware synapses or something we discussed before.
No, but the orange is no rack, right? No regular.
No, okay, but I think they still use mass or AWC or something like that.
In the no rack.
I think so.
It's like no rack at all.
I guess I still don't understand how to read these plots.
Well, it says the legend shows the average accuracy over all tasks. So whatever is on the graph is being averaged down. So
yeah.
I assume that's supposed to be the average. Say the DCOM 52.47 is the average of all the green bars.
Yeah, on top, the numbers on top in the legend are the average.
But it's on a sequence of 10 tasks. Then I don't understand.
Well, there's a
No, always at the end, you have these different accuracies.
Oh, so there is
For
no,
the task,
so you
and then
don't
you have
actually
the
see the continual part of the continual learning.
Exactly.
This is
Exactly.
post-training.
Post-training, everything.
But that's stupid. That's not the point of continual learning.
Well, this
The
is
point of
I mean,
continual learning is that you don't test at the end, but that you test in between.
Yeah, it's a matter of space. In this, we do what we say in our papers. We like to see the trend of learning, right? And we have the fixed test set, so we test every time we learn a new thing. We test the whole system, everything, so that you can see actually the trend going up. There are people showing at least the accuracy based on the things we have seen till that particular point in time. So
It's still like pretending like the point of continual learning is to at the end have learned everything. That is not the point of continual learning. The point of continual learning is that you're continually learning.
Right.
That it's an unending process.
And that implies forgetting.
And that implies forgetting, and that implies that there is no point in time where you do your benchmark.
Right.
You wanted to see it entirely over time.
Yes, of course.
But in this case,
yeah, the
really-
best thing, is to see all the accuracies in time of every task, right?
Right.
Of every batch.
that would be the
best. But then you can, but it's difficult to show in a single paper, 10 graphs over time of the accuracy, right?
Or 100, technically.
Exactly. If you have many, we have 400 batches, so it's.
I just point out that no rack is no regular. It's just regular network.
Or if you want to do it by class, also in that case you have 50 classes more. So it's tough. We have maybe new visualization techniques. Can be also.
So just as a weird aside, and then why are these different tasks so different in performance?
Well, so what I thought the explanation was that they were using some technique to avoid forgetting, plus different regularizations or sparsity regularizers.
Okay.
And in that case, maybe you tune the preservation of all the knowledge in a way such that you have this trend where you preserve more on the first task. And
I still don't understand.
So for example, if you learn the first task, then you say, let's preserve a lot of this information, then you're not able maybe to learn more about the new tasks, but you still can preserve a lot of information.
But I don't understand. So this is sequential. So this isn't time. I mean, they're talking about a sequence of 10 tasks.
Yeah, but in the end, if you look at the performance on each task, you can assume in this case that, for example, in the second part, that you have preserved a lot of information, right, on the first task.
Yes. Why?
I think that
Why is that one
they
so different from
enforce.
T7? Why is T7 so bad and T1 is so amazing?
They use memory over steps.
Yeah,
That makes a lot more sense now.
Okay, so the idea, maybe then I don't remember if the first task is different from the following one for Tiny ImageNet. I don't know if it has more images, more classes. I don't know if it's very balanced or not.
Describe here. Do you think we should, can we quickly go for a second? It's already actually
Okay, so let's just conclude about this paper. And, but yeah, they then, upon request of the reviewers, they expanded a bit with the inspections into these algorithm, and they have shown a couple of experiments on the activation distribution, somehow the parameters that I use.
I wonder whether the font size of those sub indices there is less than 3 pixels.
Yeah,
I think it's like a 3 by 3 pixel for the letters there.
Yeah, it's difficult to, if you work on a different image, then
It is really small.
you don't know if that's going to be readable or not, depending on how much is going to be squeezed in the paper, right?
Right, which is why you submit your figures in the size that they're supposed to be published in. But okay.
Yeah, maybe I don't know if this paper is the last version, the camera-ready version or not, but essentially it's still a conference. It's not a journal paper.
Yeah, it's like 8 pages, single columns, are really hard to fit in.
Yeah, that's also a reason. But yeah, so a bit more inspections, and then so with or without, using also the different, let's say, continual learning strategies, plus their own regularizer for sparsity, and see how it goes. There are a couple of more information here, and then another different task in which you don't have, because people, they were complaining about the fact that they are using essentially an oracle, telling them both during train and test, hey, this is a new task. These are different tasks. These are images belong to this particular task. These are belong to this new task. So you can disentangle essentially both during training and test. And they were using that. So the reviewers asked them to integrate a new experiment that we call it in a new instance scenario. So the idea that you have all the classes from the first batch, but then over time you encounter different data distributions of the same classes. And they've done also this experiment here on.
I had a question for you here. This idea of
this one,
like having outline
without our task numbers.
Yeah, so you could use that in your paper as well, right? And that would be kind of similar to the single instance that you're doing in Carpet, right?
Yeah, probably.
It's the same idea.
They're still working on. Yeah, the same idea can be, of course.
Because you were talking the other day about.
Yeah, of course.
This is like a good idea.
No, but there are data sets you can use. The problem is often that they're not being designed to work with these, or they are not very natural.
Right.
And you don't have, for example, in this case, you don't have temporal coherence, or they're not videos for specific objects. They're just random objects from the world.
You lose the feel.
Yeah. So
but it is still be interesting.
yeah.
So I see the description there. It says the previous one, what they did was they had 10 disjoint tasks. It's composed of 10 classes.
Right.
So you learn one class, another class, another class, another class, another 10 classes.
Right.
T1.
Yeah.
No.
No, not in a sequence. They are shuffled.
Each
It's
task is
an IID essentially training set with 10 classes.
Right, but I think the T1 through T10 were 10 runs with different sets of classes.
No.
I don't think they were sequential. I mean, from what they're saying, that what they're showing, they're considered 10 disjoint tasks, each composed of 10 classes.
Yes.
But they're learned sequential.
Yeah.
Each of these tasks are learned. This is like a common setup.
Sure, but I mean, there's 10 separate runs of 10 tasks each.
Sequentially, like the same network after you learn T1 is used to learn T2.
Right, but I mean, a total of 100 classes were involved.
Right.
Okay, so I'm looking at that T1 and T10 as not sequential, but as a run with a different set, sequentially learned, but a totally independent set.
Yeah, that was something I was complaining about the other day, in the sense that, and they're saying now that you need an oracle telling you now you have to solve these tasks of these 10. It's not a single task where you say, okay, now whatever I give you, you have to classify among 100
Right.
classes. Now we are solving the second task with these 10 classes. I give you
But
the
then
images and you
if can do
classify.
that, then you can do that average over that image, because there were 10 separate runs, 10 separate experiments under the criteria that they described.
Yeah.
Then you can average them together up in the legend.
They did that in the legend, yeah.
Right, okay, and just, we were arguing about what was, what's the pattern across, and the answer is there is no pattern.
And that's the end of it. Then there's also an appendix I didn't go through, so that's
just
my
like
bad. But
You think you can like 10 minutes over second?
okay, just to say that to say maybe it's interesting.
Maybe like the key points.
So I don't know what the second paper is. It's not open on my computer right now.
Yeah, okay. I didn't send it as well, so we
You
can
need to
check
send
that
it.
without annotation if you want.
I got a bunch of fine.
So what's this?
You want to-
paper?
you want to take over on that?
I can Google
Yeah,
it.
I can go over it.
Okay. All right.
15 minutes, that'll be
Okay.
fine.
Okay. Should I bring it up or?
Yeah, I can bring it up.
I mean,
You can just Google it and.
Okay, apparently there's a second paper. I didn't know about a second paper.
The Merrill. And
I'll get the link.
okay. So this is the paper.
So we don't have an idea scope, but I really like what I thought was interesting, like the main stuff. So it's the same setting we just discussed, continual learning, actually same task, Bermuda, Dominis, and ICIFAR. And what I thought was most interesting here,
Links in chat, guys.
so in this method, subsequent tasks are trained using the inactive nearest and filters of the sparsity network and cause zero deterioration of performance of previous tasks. So the whole idea in those methods, the elastic weight consolidation and the other regularization methods, you always have some overlap. And in this case, you're looking for a method that had zero overlap and you could learn a new task and without causing deterioration on those methods.
Specifically using the part of the network that is not used.
Yes,
Yeah.
exactly.
So effectively, we've got a partition.
Yes, effectively you have.
But the partitioning is dynamic in the sense that you don't know which
Paper's
part of
also
the
in the
network is gonna be
description. I forgot how to
by the
put it there.
learning,
Yeah, it's
Now,
dynamic.
and what part is gonna leave untouched, which is gonna be the resources for later.
Perfect.
Exactly.
That's exactly.
The nice thing is that you can use a bit of knowledge encoded in the previous weights and it's not compartmentalized completely.
You can still reuse a lot of
You
the
can
things.
see the image.
Use what you learned from the
Yeah.
previous task,
But-
but you're not allowed
To
to
change.
change whatever the previous task has changed.
Right,
Yeah.
right.
Right, okay.
And
I get it now.
in that sense, it's very similar to the continual learning by changing the architecture, like a progressive neural
Yeah,
network
yeah.
would be. But in those cases, you're just adding stuff to the network, while in this case, you're not adding stuff. It's the same network.
Right.
You're just identifying where you can change that won't cause an impact to the
Right.
previous one.
So the network still has a fixed size.
Yes.
Yeah.
So this is interesting. And he talks about forgetting. That's the interesting part. So concept of graceful forgetting. Sorry. Where am I? Idea that's preferable to suffer a small amount of forgetting in a controlled manner if it helps regain network capacity and prevents uncontrolled loss of performance. And okay, and he shows empirically that his method, continuous learning neural pruning, leads to significantly improved results over current weight elasticity-based methods. It's actually a very good paper. It's a pity to do it in 10 minutes, but I'll go over the main steps.
Yeah.
And then maybe at some point else you can.
If you think there's a lot of meat there, then, why, I mean, I think,
Yeah, I still,
Yeah,
I don't
we
know
can
when
have
you
a-
have time, but I'll just go remains that maybe we can do it like in detail at some point.
Yeah, in another journal club or something.
Because we already have something next Friday, so I was worried.
Well, but
We can, well, I'll just go. All right, just go. What are the main steps here? Let's see.
I will go directly to the image, the main image.
The main image? Okay, that
I
makes
think
sense.
that's really explaining this idea of.
Yeah. I read it in black and white, so I couldn't see the image, so I had to read the paper, so I didn't see the images. So he explains the difference between, I don't think this is relevant, but he explains the difference between sparse weights and sparse activation. So in this paper, he's calculating, he's using sparse activation instead of sparse weights.
Yeah.
And so here is the method actually. So this paragraph explains everything. So this and that one. All right.
Yeah,
Yeah.
essentially, in the image you can see that on the right there.
Right.
You want to use the gray neurons. and
Yeah.
lights.
So he divides the weights into 3 parts. One is the weights which are active, and they connect active nodes to active nodes. So this he called active weights. So he's not going to touch those. And then he has 3 weights, which are weights that connect active nodes to inactive nodes or inactive to inactive. So these are 3. So if you change those, they're not going to impact the first task
Yeah.
anyway.
So the gray.
They're the gray
weights
ones. And he has a third one, which is the interference weights that connect inactive to active ones. And
dashed red the lines there.
where the dash?
Why are they called interference weights?
If you change them, you could impact on the activation
Why?
of the
Right.
neurons.
If they're already active on the other side.
But
Not
yeah,
it
if it-
says they are not. They're not.
differentiate between the last 2 classes. What is the difference between?
so 3 is inactive to inactive or active to inactive. So it's not
Why is
impacting.
active to inactive not interfering?
Because the next one is going to be inactive anyway. So if you change this, it's not going to change the next one.
I don't understand, but changing that weight might make the post neuron active. Is that not interference?
That's a good
No
point.
interference. You can use that to you can use that information of the or not. It depends on the new training. That way can be learned when you learn a new task, but that's up to the optimization.
I don't understand the differentiation between those two. And it seems fundamental to understand.
Right. Yeah. No, yeah. Of course.
So,
Let's.
yeah.
Why is it free when there is an activation and it's interference when there is no activation?
So inactive to inactive, it's free anyway, right? That's
Yeah,
okay, right?
right.
Okay, your question in the active to inactive, why he's calling it free? I don't answer. We can go over and read it. Let's see. These are the nodes in blue. Next, we have weights which connect any node to inactive nodes, which we call free. So any node to inactive node is free, and then he makes a differentiation here at some point, right?
Yeah, but I don't know if this is creating a confusion, but I think active in this sense is not like they are firing all the time. It's just that the modulated activity can lead to recognition of particular pattern. They are, let's say, the blue neurons there. They don't have to fire together. They are just allocated to recognize several patterns of the first task, right? And you don't want to interfere with
How
them.
do you know that? I still don't understand.
The idea there is you train the entire network, then you prune it to just having the
What are you pruning? Nodes or weights?
So you're pruning weights. So I'm going over to that
So
side.
there's a
But
threshold, because all the weights are changing.
Yes, based
There is
on
a-
the neuron importance, I guess, even in this case. if I
yeah,
remember
based on
correct.
so
So if you have a
Is
good
that based
activity,
on the same metric, like the total weight of the gradient?
I think no, it's based
No,
on
it's
the activity. So how active has been in the recent period.
I'll get to that. It's like the next page. But so this paragraph, it's what note we can split free weights in 2 groups. So the first group, he says, connect active to inactive. And these are the weights that take advantage of previously learned features and are responsible for transfer line. And then you have the weights which are from inactive to inactive and then form completely new pathways.
Why are nodes that don't have postsynaptic activation. Why are those responsible for transfer learning? I don't understand. What does that have to do with transfer learning?
Well, the fact that you have already learned to recognize, let's say, the two blue dots in the first layer,
Right.
these learn to recognize a particular pattern, right? Let's say. Then the upper right gray neurons, they can exploit this information or not. And this will be a case of transfer.
I think it's a case where when you could decide you could do
Well, that's what they call transfer learning, because transfer learning in like cognitive science is something completely different.
Well, I don't.
It's where you're allowed to recruit what has been learned on the previous layer, and you say you're free to use that one too.
Yeah,
Right.
exactly.
So it's not like, these things are totally disjoint. You're saying, if this thing learned something that is of interest to you, you can too also can use it.
Yeah. Exactly.
You're not allowed to change it.
Yeah.
You're just saying you can form a connection and make use of that information.
What are the lines here you were saying? I didn't see the picture when I read the paper. So the dash ones are what?
Ways that you don't want to change it because they could lead to interference.
So the dash are the interference.
So if you tune one of, they can impact on the activations or the
Right.
the activity,
Right.
The blue are dash.
disrupt the activity that you actually
Yeah.
need
Yeah.
for getting your output in the dash.
Yeah.
Right.
Are all dash lines the same color or no? They're two different colors.
There's three
Yes.
colors.
That's not daltonic friendly.
So let's clean that. Right.
I can't see that thing.
Right, so in that sense, the blue lines are central, and the red lines can interfere, and the gray lines, they thus called free.
Yeah, but so with this idea, the problem we'll see later if we can reach that point in the experiments is that it's you quickly saturate the entire network this way
Right.
because you essentially freeze quite a bit of amount of even also because with pruning and other techniques with sparsity you don't reach the same level that we opt of 2% or less
So that's where the forgetting kicks in.
Yeah.
So I'll just move on to the method. So the whole method is after the end of the training, he's gonna prune the network based on the activations, right?
Right.
So he has his threshold and he's gonna essentially prune the connections.
Does he retrain after that before we go?
No, he said he could. So usually pruning methods retrain. So in the end, he does an experiment where he retrains, but in this case, he just prunes.
Okay.
So he
It's
prunes.
hoping not to lose too much performance.
Right.
Special pruning, of course.
Yes.
Yeah.
So this is the core of the method. Do you want to?
I think it's nice. You have a very decent algo representation. You have zero forgetting, but the problem, also on CIFAR, it has a quite small problem. After the fourth batch, I've seen that you reach the saturation of the network. So I don't know if this is really scalable. And I like more the
By
idea
saturation of the network, that means that
always
you
been
cannot lock
allocated.
anything. So essentially, you have just robbed. Like you've just taken from the future to feed the present. I mean, you've built a network that eats up all the resources in the learning now, so that with no forgetting. Right?
Yeah,
So,
exactly. And then they have introduced this idea of graceful forgetting, and in fact, I don't know what they changed at that point, but essentially they start to change some connections, right?
Yeah, I think they changed that threshold probably. I'm not sure that's it. We then pick the modules. Yeah, I think it's it. We specified the pico modules using the highest activation threshold data.
Okay. Well,
So they changed the threshold and they forget a little bit more. And then they pick the one which forget just up to a threshold they define. And that could be in the range of 0.05 to 2%. So they allow the network to forget like a little bit in order to have more free capacity for the future tasks.
that's
right, but that just increases the capacity to solve the stability plasticity dilemma.
Yeah.
Right.
So they're not actually forgetting. They're just, like doing a more shoddy job in the learning by choosing a sub-performant network.
Right, which is smaller, which has less active, less relevant
And so
data.
that leaves them more space,
Right.
but they eventually run into the exact same problem because they're
Right,
not really
right,
forgetting.
right.
No, but not, I mean, there are
That-
very few ideas on how we can model forgetting now in the context of continual learning.
I think in the previous
What
paragraph,
about
I
people
kind
waiting?
of describes it.
Educate them with
Yeah.
the of that.
In our approach.
Make them fade into non-existent.
Sparsity versus.
That would be nice
In other
to
words,
try.
after training,
But, you know,
we
people
transfer
now
sparsity.
have been,
Yeah, that's,
they're more on the opposite problem.
Right.
Try
That's-
to
that's the
summarize as possible.
Yes.
Right.
Okay. So I move on to the experiments. Pyramid MNIST, we're kind of tired of pyramid MNIST, but we can go over this plot. I think this plot is
The
easier.
allocation of the network, percentage of allocation for each layer.
What is that?
Oh, and so you can now measure how much of the network is allocated for detecting the 5 and 10, right?
Yes.
Yeah,
this is, as you said, solution capacity.
And he gets to the conclusion that as he moves on between tasks, the layers, the neurons in the first layers they are more relevant, so they get frozen, and the ones in the last layers
Yeah.
are the ones which are like flexible. And
Of course.
so you freeze the network from beginning to end. So the first ones are,
Makes sense.
yeah, which makes sense. They're acting like as feature extractors, essentially.
Right. Right. So then you can find creative ways in the later network, so when you use what information is available that's common to all the tasks.
Yeah, it's
Okay, yes, I can see that.
oh, it's definitely interesting, but I think that the usage of the neuron in this case it's not really efficient in the sense that when you don't want to have interference like in this formulation, you're actually freezing everything, and then you're not reusing the same neurons for detecting different things, right? That is the core. Yeah,
which is why
it's
they
very
run
high.
into their capacity issues,
Yeah.
which is why they then have to do
Yeah,
sacrifice a little bit to not run into that problem so quickly.
Right. There is this graph here. It's nice. Average network capacity usage per task. So I think task one ends up taking a lot, but then he forgets, and then the last task is just like using just a little bit what's left in the network. And yeah, you run into a limit like really quick.
I mean, the good thing is that it provides a principled way of setting up the training for the lower levels, and basically borrows from those only when it absolutely has to.
Right.
So rather than saying random numbers, in general, you're saying, I'm training on something, I'm training on something else, and by George, after all these tasks, these things really look important, so we'll hold on to them, and then, we've got to dive down deeper, to do some stuff, we'll borrow some away from them, but in that sense, it's continually transfer learning from one task to the next.
yeah.
Right.
But it's aligned with other proposals. So for a practical standpoint, if you have a bit of capacity, you can still add, neurons, possibly. That people have shown. It's in the end, it's quite interesting because you have zero forgetting, and with a couple of megabytes more, you can add, limited new capacity.
Right.
So that's cool. If you want to solve a practical problem without rehearsal, continual learning, that could be a way, and there are a couple of papers showing that. But yeah, I'm more interested in the idea of when you have a sparse activation, then you can have a single, like in the HTM model, where you have active dendrites, where you have the same neuron is actually used within different contexts, right?
Right.
And then to recognize different
It's
patterns.
a principled way of proving.
So it's very, yeah, exactly.
Empirically.
It's very, it's much more efficient, as you have seen from the math of the SDR,
Right.
the sparsely distributed representations, that you can go to actually everything that in a neural network like that.
Right.
That's really cool.
So it's exploring the real space.
Yes,
rather than
yes.
imposing some priors on what the locality
Exactly.
could be.
And then another observation is always that we have to keep in mind that when you do a cumulative training of the same network on all these tasks, you can fit everything. So theoretically, all this information can be fit within these limits, these model limits of capacity. We shouldn't reach these issues of capacity.
Right. Well, I mean, if you look at the I forget which of the dense papers it was where they showed how you're kind of expanding these bubbles in this hyperparameter, space. Most of these strategies are saying, how do we get to the point where these things are sufficiently disambiguated that we actually sparsely but efficiently on space. So these are search strategies.
Yeah.
So, and if you have some principled way of rapidly, expanding into the space in a way that, preserves the ability to disambiguate between these things.
Yeah.
That's really the goal here, right?
Yeah.
But in this case, I think even though it runs out of capacity, I think it's a good way of thinking of an approach towards continual learning using extra capacity. But the case is these networks are small, so eventually they will run out. But I think it's a useful way of learning. I mean, if the networks were a lot bigger, maybe you could extend the same thing to like 100 tests, 1,000 tests.
Yeah.
I don't know. I thought for me it was a good idea.
No, maybe the interesting part is that how they solve the problem that you need. It's difficult to learn with sparsity throughout it. And in this case, they solve this by saying, okay, you can use all the network and then I prune it later.
Right.
So you solve this problem in a greater extent where it's really tough to learn already sparse.
But I mean, but they use the term gracefully forgetting without actually forgetting anything. So they're not really.
Well, there's some performance degradation. I mean,
Sure, but performance degradation is not the same as forgetting. Forgetting is actually not being able to do it anymore.
Right.
Right. So if at some point, the task one would actually drop out of the set, but now you're capable of learning one new one, that would be gracefully forgetting.
Well, but maybe you can extend this graceful forgetting to you gracefully forget a little bit of all the previous tasks, and then at some point you're just going to forget one entirely, right?
Yeah, but that's not graceful, that's catastrophic.
No, but you're going to forget like a little bit at each new task learned.
So,
and then
as opposed to, you're looking at something where there's a discrete point where it's forgotten.
Yeah.
Well, in this case, there is. For example, let's say you got 80% accuracy, and then you learn task 2, and you allow yourself to have 78%, and then you learn task 3, and you allow yourself to have 76. At some point, you're just going to forget task 1. Right? If you every time you just lose 2% accuracy on task 1.
If the first task comes back again as being relevant in your space, you will reinforce it back again.
Right, but then you're gonna, if you forget everything, you're gonna have to learn it from scratch because you're using you retrain your weights to do something else, right? So
Yeah.
in this context, you have
in the sense that across all these things here, there are some weights that are going to be essentially preserved because they're common to all of them.
Right. Okay, yeah, you're right.
So you're forming a basis on which to kind of shift performance back and forth between, how accurate you are in any of these tasks. So
that basis will still be there, right? So.
Yeah. So I don't think that's unrealistic.
Right. This is a cipher, and they compare it against Zinc. That's I think Synaptic Intelligence. Am I right?
Yeah.
So they compare against Synaptic Intelligence, and it's better than Synaptic Intelligence, which is good because Synaptic Intelligence is one of the state-of-the-art models. So it's
I'm not surprised it's better.
Right. It's a different approach, like not using a regularizer. It's at the same time. So we are used to these two approaches that either you use a regularizer or you do some sort of architecture research, you add something to the architecture. And for example, Vincenzo do both at the same time. He's really, he do both architecture research and regularization. And this case is different because it does none of both, let's say. It doesn't add the regularization and it doesn't do architecture search. I mean, as in adding to the natural. So it's like a third approach. That's how I saw it. I don't know if you saw it in the same venue.
Well, I would define it as architectural.
You define as architectural approach, okay. But within, you don't expand your architecture. It's within the same architecture, right?
But you change somehow you compartmentalize you use just some weights for a task, then yeah, it's kind of an architectural approach, structural.
Right.
And you can impose other constraints on top of it. Right now, it's a, I just look at the connectivity to grade these things. You could put other priors on that if it made sense to do so. As to the choice, okay, I've got end nodes here that, I've got there will be connections to that I can exploit. Which one do I pick? Do I pick the closest one? Do I pick the one that was most recently fired? Do I, you could use this as a foundation on which to impose
Right.
More things, yeah.
Yeah.
Right, that's true.
That's a good point.
Which is nice. I mean, like strategies that are complementary rather than competitive.
Then probably you can see also this one as progressive neural networks plus sparsity. Actually, they suggested in the conclusion of progressive neural networks that you could use pruning techniques to make it better.
Right? Okay.
Yeah, because it was so tough. I mean, they
Right.
just replicated an entire network for each task, so it was very difficult and complex and not scalable. But with lateral collections to all the possible weights of the previous network, so it was exploding in terms of the dimensions. But essentially, if you think about it, it's what they do. You could think every time you encounter a new task, you're replicating the network, training, whatever you're doing, the pruning again, and then that's a new column, and you move on. So I don't.
You don't see it as...
No, it's similar. I mean, I'm saying it's similar, and that the addition here is the fact that, and it's interesting to us as well, is that they use sparsity and they have more capacity.
Right.
But essentially, I think that it's quite similar to the progressive neural network approach.
One thing I also found it interesting, I wanted to highlight, is this. Now we have, in this case, there is a measure of how much capacity you have left, you could say. Right, so at any point in time, you can kind of measure, these are the number of active neurons, and you're gonna know when that capacity is like ending. So it's a good metric to have while you're learning tests. How much can I still learn in this network? So
yeah,
I found that very interesting as well. All right.
Yes. I'm just reading that line about lifelong learning, just underneath there. And I'm thinking sort of, like at age 38, some agent will approach you. I'm very sorry, sir, but you've reached the limit on your ability to learn. For the low price of 5,098 bucks, we can prune some notes.
Oh yeah, you can see it that way. Yeah. But there is this nice property that you can choose which task you want to forget. Right. You want to forget this, all right? Let's prune those.
Yeah, but that's differently graceful and ungraceful.
I have a question for you, maybe related to those papers. So the proposal you have on continuous learning, is it somehow related to first paper, second paper, or is it like
both? I guess.
Both, I guess. All right. So maybe I'll wait for you to present. No worries.
Okay.
I
don't want to rush you. Just curious, actually.
Yeah, we can discuss
on statute.
Cliff notes? What's it?
Oh, I'm sorry. It's because the condensed version.
The condensed version.
Yeah, there's
30-second speech. What's it? There's elevator pitch.
Yeah. No, I mean it's in English class you're reading. They tell you to read these books, these tomes. And so this company came out that actually would sell you, here's the condensed version of this thing, so you don't have to spend the time reading this.
That's cheating. Huh?
Well, but they essentially summarize it for you, which means you don't get the personal experience of learning and forming your own opinions. It's just that so you can answer questions on a test.
They also do give you interpretations of
Yeah, but then you have their opinion, not yours.
A user.
I use it.
Yeah.
I mean, that's the difference between learning and education, right? Which is exactly that.
Which is
having an education is not knowing anything. It's having gone through the process of learning stuff and then forgetting it. That's true. That is education. So, none of these networks are educated.
Having gone through the process of learning and forgetting.
These guys seem to be learning.
All right.
Forgetting pretty fast. But I think the paragraph up there, he was saying that if you go, it seemed like he implied that if you go back to the original task, you can recover some of the stuff that you lost previously.
It does? I don't know.
The page,
No, recover,
with the one where you had the capacity equation.
The capacity equation.
Yeah. Was it that where it was? Yeah, up here.
Where?
Yeah,
First paragraph?
yeah, so that paragraph, it says, this sort of time tuning is done by retraining network for a few epochs while only updating the weights with survive sparsification. This caused the model to regain some of its lost performance because of pruning.
Where are you? Sorry, I was writing
Right
on
here.
you. Okay, thanks.
Yeah, the
Oh, but this is about fine tuning. Remember when you asked that, oh, after they prune, do they fine tune the
Right,
network?
but I mean, this would be, if you reintroduce an old task, this is mechanism to
Right.
kind of get re-proficient. on
You
it.
could fine tune on the old task, correct?
Right now.
That's a good point.
fine tune on the old task.
After you prune, you could like rerun like the old
But
task
you
a
need the
little bit.
data. You need the data again.
Yeah, you need it.
But that's not really.
Well, yeah, it is.
You need to get back on your motorcycle
Yeah,
and
I
learn how
mean-
to drive again if you haven't.
No,
been
I
riding
mean
for
it's
5
not
years.
really in the let's say normal continual learning setting.
Well, no,
You don't want to store any patterns. You don't want to see again the same tasks.
no, but I mean, if you're in the environment, if you reintroduce something that is similar enough that it.
Yeah,
would make
yeah,
sense
that's true.
distribution.
That's true. Yeah.
So that, I mean, nothing is going to be exactly
Okay,
identical in
Yeah,
any case.
that's true.
Okay, Kevin's not thinking about Premier Elements, he's thinking about AGI.
Yeah. No, but also in our core 50, for example, we see again the same classes, even in a different distribution,
Right.
something like that. So maybe it's true that you can fine tune. But yeah, I don't know if that would lead to better performances, because in general, especially with gradient descent, you tend to really overfit on the specific data you are looking at.
Yeah.
So for example, I have the same class, I have all the weights
Right.
recognizing
Well,
that
I'm
class.
just looking at this thing as, you train up to a certain point, things have kind of gelled a little bit.
Yeah,
But, I mean, there are certain games that I play that if I haven't played it in a couple of months, it takes me a while to kind of get back, to do that because they've been presumably harnessed for other things. But I have a sufficient plasticity that I can come back to maybe 90% of what I was playing
Yeah.
continuously type of thing. So it's that kind of behavior I'm looking at as this thing reflecting, as opposed to higher order AGI. But it should at least have this property so that you don't get into a bind where you're literally at full capacity and
Yeah.
can get nothing more. There's got to be some kind of trade-off among some of these things. Now, the schema where you say, hey, in reality, we have this huge network. I can remember, incidents back when I was 5. How do you want to represent that? That's maybe a different thing. I'm looking at, skills that go away that can come back again, as opposed to having, iconic memories that, because of emotional fixing and tagging and whatnot, I could replay for the rest of my life. So there's different things. But I like this thing because so many of these things that use regularizers are using kind of these global priors that don't reflect the experience. There's an assumption that this thing somehow has a learning capability to it. But if somebody says, what I've learned is what's embodied in the network, and operating on that level means that I'm truly affecting what was learning, and using a fairly simple principle that, what is useful, hold on to, what is not, repurpose. And at the same time, try to not have everything fire at the same time for the homeostatic, argument. What do I know?
Well done. All right,
Anything else?
that's all good. Cheers, everybody. Woo.
Yeah, right.
Okay, Matt, I think we're done.
Okay, thanks you guys. That was a long meeting.
Yes.
All right,
True.
I'm turning you guys off. You're offline as of now. Okay, now I'm gonna turn this off. But why don't you guys do me a favor and take the double back for me? Okay, turn this off. Okay, this is the wrong camera. Let me do this. Thanks for watching. First of all, thanks for watching. Second of all, I hope this is not mirrored. Like and subscribe. And we'll keep doing it. We're gonna keep live streaming. What is up with the chat window? I can fix it, hold on. Or I'll just break it. Or it's broken, whatever. I don't know. Anyway, thank you for watching. I think there'll probably be another research meeting on Monday, which I'll live stream. I think Marcus is gonna do something. I think there will probably be a research meeting on Wednesday. I might even be talking about something then. I'll plan them out. And then definitely something on Friday. So I hope you enjoy these meetings. Please do me a favor, like I said, like and subscribe. That's the best way to support right now what we're doing. We're live streaming all of our research meetings, all of our journal club reviews. The best way to help us is like and subscribe. So please take a moment out of your time and do that right now. And I will leave you alone. Here comes some chats. Here, everybody all of a sudden is saying thank you. You're very welcome. I'm really happy to be doing this sort of thing. I love being transparent about scientific discoveries and research. I think it's a wonderful way that we can just put all of this out there for anyone to consume and build upon and try and work with and understand. We want to understand how the brains work and share everything that we've learned so far. That's what we do here at Numenta. Take care. See you guys on HTM Forum. Otherwise, I'll see you live streaming probably Monday. I probably won't be streaming the rest of the day. So have a great weekend, everyone.